reversible. Reversible reaction. So one of the first thing is, if I have a reaction like this, say A plus B to give us C, then I have A plus B, okay, to give us C. So in chemistry, a reaction like this we say is irreversible because the sign tells us that the reaction goes only in one direction. But if you have a reaction that has this sign, we say the reaction is what? Is a reversible reaction. Okay, reversible reaction. So when we say it's a reversible reaction, what do we mean by saying this reaction is a reversible reaction? What that simply means is that we have two reactions here. We have reaction X and reaction Y. The reaction X will be the forward what? Will be the forward reaction. Forward reaction. Y reaction Y will be the what? The backward reaction. Okay, so that's the forward reaction and the backward what? The backward reaction. So that tells us that for the forward reaction, if I have to have products, okay, and reactant, product and reactant, or if you like, so that you can put it in proper orientation, I have reactants, reactant and products. So for the first reaction, this is forward reaction, my reactants will be A and what? A and B, but my product will be C. Okay, but for the backward reaction, my reactant will be C and my product will be what? A and what? A and B. Can you see that? So that tells us that this reaction is a what? A reversible what? Reaction. Okay, and so when we say reaction is a reversible reaction, this sign, okay, that is the sign that shows that the reaction is what? Is reversible. Okay, so you have the arrow going forward and what? Going backward. It shows that the reaction is reversible. Then also in chemistry, we'll talk about dynamic equilibrium. Dynamic what? Equilibrium. Dynamic equilibrium. Okay. Now, a dynamic equilibrium can be attained by any reaction that is a reversible what? Reaction. So we are saying that a reaction is reversible. It will get to a point where you have the rate at which the forward reaction is taking place will be equal to the rate at which the backward reaction is taking place. At that point, at that instance, we'll say that the reaction is at what? Equilibrium. And that is only possible for a reaction that is what? A reversible reaction. Okay, let's say we have this reaction, A plus B going to C plus D, and it's reversible. Forward X, backward Y. We are going to get to a point where an equilibrium will be achieved. At that point, we said a dynamic equilibrium is set up. So for a dynamic equilibrium to be set up, what are the conditions that must be fulfilled before we can say that a dynamic what? Equilibrium is set up? What are the conditions that must be fulfilled? Number one, equilibrium is only possible in a closed what? A closed system. Equilibrium is possible only in a what? A closed system. So what is a closed system? Let's assume that I have a bottle of Coke, okay, soda, a bottle of soda. Of course, you know how a bottle of soda is, okay? I have soft drink inside. If you've ever attempted to hurriedly open a bottle of soft drink, what you find, especially when you have shaken the bottle, what you find out is that it foams out, right? It foams out. So when it foams out and you decide to cover the lid again, what do you normally notice if you've ever noticed that before? When it foams out and you cover the bottle, what will be observed?
Um, to a reaction.
Yes, I'm talking about a bottle of soft drink that you open. When you open a bottle of soft drink, you see that the drink will fizzle out, like it foams out, right?
Mm-hmm.
Now, when you cover the lid
Mm-hmm.
and you decide to cover the lid, what do you observe?
It's nothing. It still feels more like the air is still in the bottle.
Okay, so usually when you close the lid, okay, the foam settles down, it goes back into the bottle, it settles down, everything dies down. Okay, now when we say a closed system is a system that does not exchange matter between itself and the environment. That's a closed system. Okay, between itself and the environment, there is no exchange of matter. Okay, and sometimes to exchange of energy. You say that is a closed one, a closed system. So in a closed system, if I open the bottle of Coke, open it and throw the lid away, okay, the carbon dioxide dissolved in the soda will only flow in one direction. That the only direction is that drinks will keep going out of what? Out of the bottle. That's the only thing that will happen. Drink will keep going out of the bottle in one direction because the bottle is open. Now it's an open system. But the way to close the bottle, will seal up the lid, okay, it becomes a closed system. So what you have is that you have a liquid here, and above the liquid, you have what we call the gas phase, then you have the liquid phase. That is what happens in a bottle of Coke. So that when you open it, that's why you usually hear that sound. Because the gas pressurized here want to escape. So that means they go in one direction. So, but if you have a closed system here, the gas on the surface of the liquid will dissolve into the liquid. Then some liquid will also evaporate and turn into gas. So you have gas turning to liquid, liquid turning to gas turning to liquid, liquid turning to gas. So to get to a point where an equilibrium will be what? Will be reached. Okay, so when equilibrium is reached, we say that the rate of forward reaction, is equal to the rate of what? The rate of backward reaction. So at that point, we say a dynamic equilibrium is what is achieved. Then the third thing, when a dynamic equilibrium is set up, okay, the concentration of all the species, by species we mean the reactants and products, the concentration of the reactant and products, okay, remains what? Constant. Remains constant. So these three conditions will give rise to what we call dynamic what? Equilibrium. Dynamic equilibrium. So apparently we are saying that if a system is at equilibrium, the rate of forward reaction is equal to the rate of backward reaction, and the concentration of A, B, C, and D will remain what? Unchanged, or the ratio of the concentration will remain what? Will remain constant. At that point, we say that a system is at equilibrium. Now, the question is this: if something is at equilibrium, let's say, for example, you have a seesaw like this. Okay, a seesaw. Here I have one block. Okay, on this other side, I have one block. Now this system is stable. Okay, so we say it is at what? Equilibrium. Like you have your moment in physics, equilibrium. So let's assume this is my reactant on this side, and here I have my product. Okay, on that side. Good, they are balanced. We say the system is at equilibrium. Okay, now if I decide to alter this equilibrium, what can I do to alter this equilibrium? What can I do to alter the equilibrium?
I didn't hear your question, sorry.
Yes. What can I do to alter this equilibrium?
So maybe change the temperature.
No, just speak generally now in terms of
Oh,
this years.
so you can make the reactant more than the product.
Okay, good. If I make the reactant more than a product, I'm going to be getting something like this, isn't it?
Yes, sir.
Maybe I added an extra block here. This is what I'm going to be getting, isn't it? So
Yes.
here we say that this equilibrium is distorted. We have a distorted what? Equilibrium. Now the question is, big question I want to ask, can equilibrium be restored?
Yes, sir.
Okay, so the question is yes, or the answer is yes. So this particular one here, this is stage 1, this is stage 2. What can I do to stage 2 to restore the equilibrium?
So I'd remove some of the reactant or add more of the product.
Fantastic, Adesra. Fantabulous. So I can what? Remove the reactant, part of the reactant, right? Or I can do what? Add to the what? To the product, right?
Mm-hmm.
Good. Now, when a chemical reaction is taking place, an equilibrium is achieved, then the equilibrium is distorted by changing conditions of the reaction, like temperature, pressure, concentration. So those are factors that could affect equilibrium. So if you want to alter equilibrium, you can change those factors. Okay. So, but if you want to restore equilibrium in a chemical reaction, let's assume that we change the concentration of the reactant, we added to the reactant. Okay, equilibrium is going to restore itself. Okay, back to a state of balance. But how will the reaction restore itself to equilibrium? Normally, what reaction does is this: the reaction will use the reactant to form more what? More products. Are you getting my point? So you
Yes.
said that we can either take away the reactant. So how the reaction does that is that the reaction will use the reactant to form more what? To form more product. So it will take out of this to form more product. Okay, so to restore the equilibrium, the reaction, okay, has taken part of the reactant to form equilibrium. So I have a block, and let's now say I have half, because I taking half of this to put to the what? To the reactants, to the product side. So now I have 1.5 on this side, I have 1.5 on the other side. Okay, so equilibrium is what? Is restored. This is restored what? Restored equilibrium. So why the reaction was restoring itself, you notice that materials were moving from the reactant to the what? To the product side. So it looked as if things were going to the what? Forward direction. So we'll say that equilibrium favors what? The forward direction. Equilibrium favors the forward direction because reactant was being used to form what? To form product. So equilibrium was favoring the forward direction. So if the opposite was taking place, such that materials were moving from the product side to the reactant side, then we'll say that equilibrium favors the backward what? The backward direction. So those are the languages that we are going to be using. Okay, so when we say equilibrium favors the forward reaction, what does it mean? Equilibrium favors the backward reaction, what does it mean? Okay, so when you say equilibrium favors the forward reaction, okay, so when forward reaction is favored, forward reaction, when forward reaction is favored, what does it mean? It means that equilibrium shifts to the what? Shifts to the right. Okay, and that simply means more products. more product is formed. Okay, what we call yield, more yield is formed. So when we say equilibrium favors the backward reaction, favors backward what? Backward reaction. See, if equilibrium favors backward reaction is, if equilibrium favors the backward reaction, what does that mean? It means that equilibrium shifts to the what? To the left. That's what it means. Equilibrium shift to the left. Okay? And what does that mean? It means that the product breaks down to form what? Breaks down to form what? To form reactant. To form reactant. That's what it means. So you need to understand this language thoroughly. Okay?
Okay.
So now, having established that, let's just review quickly. Review factors that affect equilibrium, that affect position of equilibrium. Okay, number one, what do we have?
Concentration.
Okay, two.
Pressure.
Pressure. Three, what?
Temperature.
Temperature. Okay, good. So if you look at this, somehow it relates to factors affecting what? Affecting rate of chemical what? Reaction. But out of those factors for affecting rate of chemical reaction, you know we have catalyst. But for equilibrium, catalyst does not affect the position of equilibrium, because if you add a catalyst to a reaction at equilibrium, the catalyst will favor both forward and backward reaction. It will increase the rate of both forward and backward reaction. Okay, so catalyst does not alter equilibrium. It favors both the forward and the backward reaction. So the catalyst is basically unbiased. Okay, in this reaction, the catalyst is what? Is unbiased in the what? In the reaction. The catalyst is unbiased. Okay, so let's now see how these factors affect the position of what? Of equilibrium. Now, let's introduce a principle that will guide us to understand how equilibrium could be what? Could be restored. Okay, so there is a principle called the Le Chatelier principle. Le Chatelier's principle. Okay, the principle just explains how equilibrium is restored. Okay, the principle tells us that if there is a change in any of the factors affecting equilibrium, if there is a change in any of the factors affecting what? The position of equilibrium. Okay, it tells us that equilibrium will restore itself by cancelling the effect of what? Of the change. Equilibrium will restore itself by cancelling the effect of what? The effect of the change. That's what that law basically is telling us. If there is a change in any of the factor affecting position of equilibrium, equilibrium will change in such a way as to what? As to restore itself. That's what the law, the principle says. It's called the Le Chatelier principle. So what that's simply saying is this. If I alter, let's say, temperature, we're looking at temperature now. Temperature. If the temperature of a system is increased, okay? If the temperature of a system is increased, what will equilibrium do in order to restore equilibrium? Equilibrium will reduce the what? The temperature. That means equilibrium does the opposite of the change that alters equilibrium. The change that alters equilibrium here is increase in temperature. So in order for equilibrium to restore itself, equilibrium will attempt to reduce the temperature. Then it comes back to restored equilibrium. If it was concentration, if concentration is reduced, for example, what will equilibrium do? Equilibrium will attempt to increase the concentration in order to restore equilibrium. The same thing happens to pressure. If the pressure of the system is increased, what will equilibrium do? Equilibrium will attempt to reduce the pressure. So basically, if any factor comes in to alter equilibrium, equilibrium will do the opposite of that change in order to restore itself back to equilibrium. That is what Leclerc principle is all about. That principle explains how equilibrium is restored after it has been altered. So the next question we want to ask is, okay, so how will equilibrium attempt to reduce or change temperature? How will equilibrium attempt to increase or change concentration? How will equilibrium attempt to increase or decrease pressure? So we'll take each of these factors one after the other and we'll explain that. So the first factor we'll look at is concentration.